This is the first lecture on Text Unit 1 and is the first lecture for the course. Unit 1 concerns the basics of science. One of the first issues that the text addresses is the scientific method. I'm going to assume that everyone learned in high school that the scientific method takes data gained from observations which are often made in a controlled environment in the form of experiments, and that this data is used to formulate laws, hypotheses, and theories. I'm assuming, again, that you've all heard that before. What is important is that to be able to determine the difference between a law and a hypothesis and/or theory. I'll begin by describing what a law does. A scientific law describes a great number of observations. So, for example, Boyle's law describes the behavior of gases. Boyle's law says in words that as the pressure on a gas goes up, its volume goes down. This is a description of many observations of the behavior of gases. The law of gravity describes how gravity works. It's often stated in words, what goes up must come down. This is again a description of a large number of observations about gravity. The law of conservation of energy says that the amount of energy is the same. Energy can't be created or destroyed. But the energy can take different forms. This is a description of many observations about energy. Okay, so again, a law describes, or sometimes summarizes, some say, a great number of observations or experiments. Hypotheses and theories, on the other hand, explain a great number of observations. A hypothesis explains a great number of observations. A theory is just a hypothesis that has been suggested through successful experimental testing and successfully predicts future observations. For example, the theory of gravity explains why gravity works. The law of gravity states how it works. The theory of gravity explains how it works. The theory of gravity was developed by Einstein and describes how masses curve space and therefore attract each other. The theory of evolution explains how life forms that currently exist arose from life forms that existed previously. Exercises and readings will be available online on laws, hypotheses, and theories. All right, let's continue. The next topic in Text Unit 1 is the topic of the science of chemistry in particular. Chemistry is the study of matter, where matter is something that has mass and takes up space. You have all probably heard and remember that matter comes in three physical states: solid, liquid, and gas. Solid has a definite volume and a definite shape. Liquid has a definite volume but no definite shape. It takes the shape of its container. And a gas has no definite volume and no definite shape. A gas takes the volume and shape of its container. You've probably heard the three physical states of matter described as the three phases of matter. We'll use the word phase to mean something else in this course. More on that later. Properties of matter can be grouped into two categories: extensive or intensive properties. An extensive property of matter is any property that depends on how much substance or matter there is. Examples of extensive properties properties are mass or weight and volume. Both of these increase as the amount of substance increases. Intensive properties, in contrast, do not depend on how much there is. Typically cited examples of intensive property are temperature. Any amount of water can be hot, for example. A drop can be 80 degrees, or a gallon of water can be 80 degrees. And another intensive property is pressure. Other properties such as color are intensity properties, for example. They do not depend on how much there is. Information about matter is gained from measurement, and measurement implies units. We'll use metric or SI units in this course. SI is an abbreviation for two French words I do not remember, but it essentially implies metric units. The table below is taken from the text and displays SI quantities such as mass, length, and time. These are base quantities. The base unit of mass is given as the kilogram. In fact, for chemists, that's often the gram, and the symbol is not kg, but g. Base unit of length is the meter. Base unit of time is the second. You'll find in the text in Unit 1, Table 1.1, which is a list of the SI prefixes. On the left-hand column, you see the prefix in an abbreviation, and in the right-hand column, you see the magnitude. The association of the prefix nano, for example, with 10 to the negative 9th means that 1 nanometer is 10 to the negative 9th meters. And 1 kilometer, for example, is 10 to the 3rd meters. You should memorize Table 1, which is to say memorize each prefix and the magnitude that goes with it. And remember that 1 megameter is 10 to the 6 meters, or 1 megagram is 10 to the 6 grams. Unit conversions between kilograms and grams and other quantities and prefixes that appear in the table can be accomplished by using unit conversion factors. For example, here's an example of unit conversions using Table 1.1. A typical sort of question is how many kilograms in 327 grams? First, in a problem like this, you write down what you know, then a unit conversion factor. The numerator of the denominator of the conversion factor are equal. Set up the conversion factor so units of grams in the numerator and denominator cancel. For example, we start by writing down 327 grams, which is what we know. This is multiplied by this unit conversion factor. In the unit conversion factor, we have the numerator of 1 kilogram, and in the denominator 10 to the 3rd grams. Note that the numerator and denominator are equal. 1 kilogram equals 10 to the 3rd grams. We have that from Table 1.1. A kilogram is 10 to the 3rd grams. In the unit conversion factor, kilograms appears in the numerator and grams appears in the denominator. Terms of grams algebraically cancel, and we are left with the units we are asked for, which is kilograms. All right, now try converting the following. Try these conversions using Table 1.1 of the text and unit conversion factors like you saw on the last slide. At this point, I recommend stopping the lecture and attempting these conversions on the piece of paper. You should have table 1.1 of the text open so you can look at it, since I don't expect that you have it memorized at this point. When you are ready, start the lecture again and resume. Here are solutions to the conversions on the last slide. 128 kilograms is to be converted to grams. The unit conversion factor puts 10 to the third grams in the numerator and 1 kilogram in the denominator. Note again, the two things in the unit conversion factor are equal and must always be equal. 1 kilogram is 10 to the third grams. 1 kilogram appears in the denominator, so it cancels. 10 to the third grams in the numerator. The answer when we multiply is 128,000 grams. If we are converting grams to decagrams, the table tells us 1 decagram is 10 to the 1 grams. 10 to the unit conversion factor has 1 decagram and 10 to the 1 grams. 10 to the 1 grams is placed in the denominator to cancel grams in the numerator here. 1 decagram is in the numerator of the unit conversion factor, and those are the units of the answer. Note when you write down an answer, it is important to always write down the units. 56.78 liters can be converted to milliliters with this unit conversion factor. If you look at the table, it says that 1 milli is 10 to the negative third, so 1 milliliter is 10 to the negative third liters, or 1,000th of a liter. 1 milliliter appears in the numerator because milliliters are the desired units. 10 to the negative third liters appears in the denominators because we are trying to cancel liters. Note that the numerator and denominator, as always, are equal. If the numerator and the denominator are not equal, you should stop doing the problem and set the problem up so the numerator and denominator are equal. The solution is 56,780 milliliters. In the last one, meters are converted to kilometers. The prefix kilo implies 10 to the third, which means that 1 kilometer is 10 to the third meters. In this calculation, kilometers is in the numerator of the unit factor, and 10 to the third meters is in the denominator. The solution is 0.0236 kilometers. Feel free to stop the presentation, go back, and try again if you like, before continuing onward. Alright, let's try one last conversion. How many kilometers are in 4.21 gigameters? Take a moment to work that on your own before you peek at the solution at the next slide. Stop the lecture and attempt the problem now before moving onward. The solution of the problem is two conversions. Convert gigameters to meters and meters to kilometers. Here is the problem done in 2 steps. First step, 42.1 gigameters is converted to meters. The unit conversion factor has 10 to the 9th meters over 1 gigameter. Note that giga means 10 to the 9th in the table. The solution is 4.21 times 10 to the 10th meters. The next step, 4.21 times 10 to the 10th meters, is converted to kilometers by multiplying it by this unit conversion factor. This unit conversion factor is one we've already seen. 1 kilometer is placed over 10 to the 3rd meters. Units of meter algebraically cancel. And the solution is 4.21 times 10 to the 7th kilometers. This problem can also be done in one step. here is the number we start with, 42.1 gigameters. That's multiplied first by a conversion factor which converts from gigameters to meters. And then, since this times this has units of meters, it can be multiplied by a conversion factor that converts from meters to kilometers. Note that we get the same answer, and note that the two conversion factors in our multiplication are the same conversion factors we've used before. Gigameters cancel, meters cancel. In all cases, the numerator and the denominator of each unit conversion factor are equal to each other. Alright, this concludes Lecture 1, Part 1. When you are ready, move on to Lecture 1, Part 2.